Welcome everybody. It's the top of the hour. Welcome to the 10th webinar on CPT. And today we will discuss once again Seismic CPT, a continuation of the webinar that we did in January of this year, because at that time we were not able to address all the questions that were raised. With that, I will now introduce Troy Chips, the CEO of Eijkelkamp North America.
Thanks, Gerald. Good morning, everybody. It's glad to have everybody here on our 10th webinar. It's amazing. It's gone by that fast. And on Seismic CPT, for this 10th webinar, we have Rob Lukacs, one of our partners up in Canada, has put together some questions on Seismic CPT and sent those over to Gerald Verbeek, which is our technical expert for CPT. And the two of them have prepared a presentation, a little question and answer that they'll go over with everybody. Remember, we do this every month. We do it the second Tuesday of every month, 11 o'clock Eastern. If you have a topic that you would like us to cover, please let us know, reach out, send us an email, and we'd love to put something together for everybody. With that, Gerald, Rob, looking forward to it.
Hi guys, hi Gerald, Troy, thanks for having me back again. It's good to be here for a second time. So yeah, what I've done, what Troy mentioned, we've prepared a list of questions that were sent over to Gerald, and I guess we had so many good questions that we did this as a round two. But as a recap, in case anybody wasn't on the call on our last webinar, webinar 9, just Gerald, if you could summarize quickly, how does Eijkelkamp GeoPoint's SCPT technology work?
Thanks, Rob, and welcome everybody. Great that you're here. Let's first start quickly talk about CPT, because Seismic CPT is nothing more than an extension of CPT. And CPT, what we do is we push a cone in the ground, as you can see here on the right-hand side of your screen. Whether we use a rig or a crawler or a standalone pusher, it doesn't make any difference. You push a cone into the ground. You do that at a standardized speed of 0.8 inches per second or 2 centimeters per second. And that cone that you see enlarged measures the tip resistance, the pore water pressure, and the sleeve friction. That cone is very much standardized. The dimensions of the cone, the length of the cone, all of it is standardized, and it is described in ASTM D5778. The ISO standard on the same topic of cone penetration testing prescribes pretty much the same dimensions of that cone. Now, what we do differently when you have Seismic CPT is that is what is described here in this chart. We're still pushing the cone into the ground, although now the truck has miraculously moved from the right side to the left side of the screen. And we stop about every meter. And at that time, we create a seismic wave by basically hitting a plate. You see that on the left-hand side, a plate that is pushed onto the ground, held down by, in this case, a tire of a truck. We hit it with a hammer, and that creates a seismic wave. And those seismic waves are then recorded, or the arrival of that seismic wave is recorded by an additional sensor that we have now in the cone. You see there on the right-hand side of the illustration, we still measure the tip resistance, the pore pressure, and the sleeve friction. But on top of that, we also have a seismic sensor. And in case of the Eijkelkamp system, it is generally speaking an accelerometer. And with that, we then measure the arrival of the seismic wave. Then using a sledgehammer, you see here some other examples. You can use a pendulum hammer that you see in the second from the left, where you just have to pull on a string, and then a hammer is dropped against the plate. But you also have automatic hammers that you see on the right-hand side, where you have a little box that just creates an impulse against a plate. But in all cases, it's important that you create friction between the plate and the soil, and that way then the seismic wave gets into the ground. And then finally, of course, we record those results that you see on illustrated, and from those results we then derive the shear wave velocity, which gives you more information about the soil conditions, but that is being done in the office and not necessarily in the field. So that in a nutshell, Rob, and all of you attending, that in a nutshell is what Seismic CPT is all about, and that's what you're doing.
Perfect. And thanks for the recap, Gerald. I do appreciate it. And I think now we'll get into some of the questions that weren't answered last time. One of the goals of us here in Canada is to bring CPT, Eijkelkamp CPT specifically, this product into the market and open it up to a few more that haven't used CPT before. And I think there's a little bit of intimidation with the data and exactly how that's managed, how it's treated. And I think with some explanation, it'll ease some minds and some thoughts there. So one of the questions is, what are common issues encountered during data acquisition in the field?
Well, that's an interesting question, but also a pretty complex question, because there are all kinds of issues that can be encountered. But I want to focus on a few major ones, and that is the seismic source. We already saw some pictures before, but to give some ideas, the seismic source can be too big, can be too close, it can be slipping. Let's just take them one at a time to give you an idea what I mean by that. So starting with seismic source is too big. You see here is a side view, a front view, and a top view of the seismic source. And I already told you, we just hit a plate, whether we do it with a mechanical hammer or a sledgehammer, pendulum hammer, or an automatic source, doesn't make any difference, but you hit that source. And then that creates waves, and those waves then travel to the receiver. The problem, though, is that you need to make sure that you know how much time it takes for the wave to travel, but also where the wave is coming from. And if you see here on the right-hand side, if you have a long beam, you really don't necessarily know where the wave is coming from. Is it traveling from the end of that beam to the receiver, or the middle of the beam? And especially when you have a long beam, the distance between the beam and the receiver, or the part of the beam and the receiver, can be different. And especially when you see a situation like this, where I have a beam that goes the full length of the truck, on the edges of the cabin, there the beam is about, say, 2 meters or 7 feet away from the seismic receiver, where it goes in the ground. But in the middle, it may only be about 3 feet away. And it obviously makes it very difficult to figure out where the seismic wave originates. And that is the issue, that the seismic source may simply be too big, so that you don't know where the wave originates. Much better situation is what you see here. We now have a left and the right, but you see there are two relatively small plates where you can create those seismic waves. But now at least you have a much more distinct idea where the wave is originating. So that's one issue. Second thing is that the seismic source may be too close. Could be creating all kinds of issues, and I'll just give you a few examples here. First one is that you may get rod interference or rod noise. What do I mean by that? It's a very frustrating thing. If you have it too close, the wave is smart, and the wave decides not to travel through the soil to the receiver, but through the steel rods, and you get what you see on the bottom left-hand side, a lot of high amplitude noise that makes it very hard to figure out when the wave arrives. Second thing is, you have so-called near field effects. And I don't want to go into too much detail about the analysis, but basically we are not, as engineers, we're not smart enough to describe in equations how the seismic wave is traveling. And that means that in the first couple meters from where the wave originates, we really don't have the equations. So generally speaking, you want to be able to have that source a couple meters, 2.5 meters or so away from where the cone goes into the ground, because there only the far field effects apply, and the far field effects we know, the near field effects we really don't. And then finally, it's a matter of accuracy. And what I've shown here on the slide are three different situations. We have an offset of 1 meter, 3 meters, and 5 meters. We have a standard test depth of 2 meters. We assume an interval velocity of about 150 meters per second. And you see then the arrival time that is indicated there. It's a very short travel time. Yeah, it's only about 15 to 36 milliseconds, thousandths of a second. So it's a short period. But we undoubtedly are going to make some mistakes there. And you see what the area is if you make a mistake of 1 millisecond. And obviously, if you have a larger offset, then you have a better feel. You make a smaller error, and that's another reason why we want to have a larger offset. So those are kind of the issues there that it deals with sources too close. And then finally, source may be slipping. So I told you it's important that you have this friction between the plate and the soil, because if you don't have that, you don't create a wave into the ground, and that means that you don't get any shear wave into the ground. And if the plate is slipping, if it's sliding over the soil, then basically you don't get any decent wave going through the soil, and then you have a problem. So those are kind of the issues that you have, that you can encounter during data acquisition.
Okay. Now, I think if you go back a slide, Gerald, that diagram of the guy pulling his hair out, you might have to send that to me. I'm going to want to use that at some point. No, that's great. So three main issues, or three sources of error or concern. Good to know what those are. Now, let's say outside of the SCPT system, you have activity on site, you have excavators, you have haul trucks, you have anything else, a tamping machine or a packer. Can that activity affect your readings if you're conducting SCPT in the field?
Well, that question I like, because it's simple to answer. Absolutely. Yeah. No ifs, buts, or whens. What you see here is a picture I took some time ago. We were asked to analyze some data, and the data really wasn't good. And I told the person in the office, well, what happened on site? And oh, nothing. Perfect situations. Only to find out that there was a truck being loaded there. Trailers were being loaded very close by, very heavy equipment, creating all kinds of vibrations. And those vibrations obviously affect what's happening in on site. And therefore, you're going to have a major problem, a major issue, because we're creating a wave in the soil by hitting a sledgehammer. But if you have a heavy vehicle going by, or if you have some material being dumped on the ground, all that creates a wave as well. And those are being recorded by these very sensitive sensors as well. And then it's going to be very difficult to analyze your data. So this is really an example that you need to make sure that if you have site activities, that you either stop your data acquisition, wait until the tractor, in this case with the trailer, has gone by, or you basically ask those people to stop their activities while you do your seismic CPT.
Okay. So this leads well into the next question, and you mentioned it. How do you know you're getting good data when you bring it back to the office?
Well, that has been a question that we've struggled with for a number of years, but about 5 years or so ago, we were able to address that question. What you see here on the screen is a typical screenshot of a data acquisition. It's pretty a lot of data in there, but on the bottom you see the four lines there. The top is the x-axis, then the y-axis, and then the z-axis. Since we are in a horizontal shear wave, you don't generally have that much on the z-axis, and then you also see in black line the trigger channel. That is what you see with some filtering, and hopefully it looks pretty good. But what we have added to that is, in the software, two major elements. The first one is that the software will automatically provide you with the first estimate of the interval velocity. And when you go out to the field, even though you don't know exactly what kind of soil you have, you should have a rough idea of what the interval velocity is. And most of the time you talk about, say, anywhere between 100 and say 300 meters per second. So that's the software gives you this first indication. If that indication is way off, then you may want to ponder what the heck is going on and what you're doing. But on top of that, the software also looks at 5 different parameters. And those parameters are shown there as the linearity, the SSP, the CCC, the SNR, the signal to noise ratio, and the PSD. And it goes in too much detail here what those things are. Maybe that's for another time. But what we are then indicating in the software is if something is wrong. And let's just take on the left side, the first line out, you see that the software indicates that the interval velocity is about 136 meters per second, which is pretty normal. But then it indicates that we have a problem with the S, which means the signal shape parameter, and a problem with the P, which is another indication of the peak symmetry differential, and a problem with the C, which means a problem with the cross correlation coefficient. Yeah, if you go the last one there, you see that there was absolutely no problem, because there you get a plus, and that means everything is fine. Now, what do you do with that? That's then, of course, the issue. We cannot, or the computer cannot yet predict exactly what your problem is. But in the manual for the software, what we have included, I've just given one indication here, for the cross correlation coefficient, we give for every single parameter a description of what that parameter really focuses on. Then potential reasons for flagging. Yeah, you see here 2 potential reasons. The site conditions have changed. Construction have started nearby. Somebody is driving by with a heavy truck, or the data collection conditions have changed. For instance, you don't have good friction anymore between the plate and the soil, and then the plate starts shifting, and those could create, then if those things happen, then you could have a potential problem with your cross correlation coefficient. And you see also on this slide on the right hand side what could be possible corrective actions. So in the field, do your testing, find out whether the program indicates that you have a good data or not. It gives you a warning what the potential reasons or the potential problems are, and then in your manual you can find how you can potentially correct that, and that way hopefully you can redo your test until you get good data. And in that case, when you go to the office, you can get the data analyzed, and you are in good shape. So that, in a nutshell, is how the system works. We don't let the people in the field just wing it or have to figure it out all by themselves. And the software gives a very specific guidance on whether you have good data or not.
Okay, so I know we're 20 after, we've got a bit of time here, and I'm wondering, Gerald, would it be possible for us to go through a little bit of the steps of the analysis of the data? I know there's a lot to that, but would we have time to go through some of that today?
Sure. Let's just take it some of the highlights there and some of the major issues that we potentially have. But I told you you do your test every so often, and what you see here on the screen is some test results that we picked up. We did a test at half a meter depth, and then we skipped apparently at 1.5 meters, but then after that, every meter, 2.5, 3.5, 4.5, we did a test. And we figured out from the squiggly lines that appeared on your screen what the arrival time was. And that is basically what we do. If we go back to this thing here, you can basically see when a wave is arriving, and that is then the arrival time that the guy in the office is using. The easiest way to figure out what the velocity is just to do a straight line approach. I'll give you an example here. In this case, with an offset of 2 meters. We use a fairly small plate, so we know that the offset is 2 meters. We don't have to worry about a large beam where the offset may vary. The initial depth was 0.5 meters, which basically means that the distance traveled in a straight line is the square root from 2 squared plus 0.5 meters square root, and it gets you 2.06 meters. We had a time of 28 milliseconds. So that gets you then the velocity that is indicated. And that way, with a straight ray approach, you could calculate all the velocities that you see there. Problem is, very quickly, of course, you see there that between 0.5 and 2.5 meters, we come up with a velocity of minus 2100 or close to 2100 meters per second. Well, apart from the fact that the value is way too high, we have a negative velocity. And you may wonder, well, how the heck is that possible? Well, you see that the arrival time is at half a meter is something like 28 milliseconds, but at 2.5 meters, it is 27.5 milliseconds. So it actually arrives earlier at a greater depth. And that is something that people think, well, that's impossible. But fortunately, there were some very smart people in the past, and Gerald Verbeek, a Frenchman, was one of those people. And he basically came up with a law that is now called Verbeek's principle, or the least time principle, that says that the ray will travel the route that it takes the least amount of time, not the least distance. And a straight ray is always the least distance, but this is the least amount of time from point A to point B. And you need to think about it this way. If you were to go from your home to, say, a city a couple of 100 miles or 100 kilometers away, you can take the shortest route, going all kinds of little streets and state roads or no highways or interstates, and that will get you the least amount of distance. But it will take you longer to get there than when you take the highway or the interstate or whatever you want to call it in your country. So what Verbeek is saying is the wave is smart. It travels the route in the least amount of time. And there was another smart guy. And since we are a Dutch company, we've always used an opportunity to promote some of our Dutch ancestors. A Dutchman, Willebord Snell, he came up with a law. He was not as smart as Verbeek, because basically he came up with something in 1621. It was already figured out about 700 years earlier by somebody in the Baghdad court. But it basically says that you need to, when you go from one layer to another, the ray path breaks. There's an angle of incidence and the angle of reflection, or refraction, that have to be taken into account. And if you take those two laws together, you basically start seeing that the rays are traveling not necessarily in a straight line. And what you see here, for instance, the red line is a straight line between the source and the receiver at 2.5 meters. But you see there that the actual ray path, which is the dashed line, deviates from that. It wants to go as soon as possible out of that slow layer at the top and go to the much faster layer at the bottom. And that is why it would actually get there faster than it would take in the top layer, where it has to travel all the distance through this slow moving layer. So what we've done now is we've given in this table on the right hand side, we have put the straight ray velocities again that we calculated earlier, which in red because you should not use that. And then you see the right way of doing it. And you see that other than at the very top, you don't get major errors, but at the very top, you get a huge error. And sometimes, depending on the soil profile, you could get those errors going down to about 7 meters or so. Now, that in a nutshell is how the system works. The problem, of course, is that to apply Verbeek's principle of the least amount of time and to apply Snell's law, where you have to deal with all those angles, because the angle that you see, for instance, here, where it comes in and then breaks at a slightly different angle, because you see at all these layers, there's a break there, different in direction. It's very hard to do that on paper. The only way you can do it on paper is with the straight ray approach, just with some simple calculation on a spreadsheet. And that's why you need some analysis software to come up with the right answers. But that analysis software is available, and we would be more than happy to provide you that software. So with that, then you can do your analysis and come up with interval velocities that are then used, as we said a month ago, to characterize the soil. So with that, Rob, that's just in a nutshell, but we give courses on this topic that takes 2 days to cover more details, or up to 2 days, but at least it gives you a flavor of what you need to do. But the most important thing is to keep in mind that the straight ray approach, the approach that you say wave travels in a direct line from the source to the receiver, that is just all kinds of a good reason why your data is not going to be accurate.
Okay, no, always a pleasure, Gerald. It's great to learn about this, and seeing it makes me want to go try it out in the field. So we gotta get this moving here. Really look forward to seeing what the Eijkelkamp GeoPoint product can do, and of course, using your expertise in making sure that we're getting the right data back to the customer.
Okay, thank you. And I hope that we have addressed some of the questions that were there. Some of it, those questions came in already, were answered by the questions that Robert asked me before. So with that, we can basically close this webinar. Thank you very much for your attendance, and I look forward to seeing you again next month when we talk about another issue associated with CPT. Thank you very much.